All right, so let me kind of get you through the lab. So this says a 10-Newton scale, usually the electronic version of it. So again, you're going to record 4 values: constant velocity up, constant velocity down, accelerating the scale upward, accelerating the scale down. Then you have a bunch of questions to answer. Now, on some of these, like on number 7, I said sketch and label. This is just a sketch. All the forces acting on the mass while it was being accelerated upward. Okay? Then, like on number 8, when's mass accelerated upward? Why did the reading on the scale increase? Explain in terms of force applied, net force, and gravitational force. Which 3 forces do you think you want to mention? Those 3.
Inertia.
Well, there was the net forces assignment that I gave back, and I meant to yell at y'all, and I forgot. But it was like that second to the last question. I said, why are NASA engineers concerned about mass? And I said, explain in terms of like opposing force, acceleration, and net force. And some of you didn't mention any of the 3. When I tell you this is what I want you to talk about, guess what? That's what I want you to talk about. Okay? Oh. Now, when you get to number 12, here's this elevator problem. So, here's the elevator, and if you're an engineer, you always plan for the worst and hope for the best. So you're saying, worst case scenario, this elevator is going into a hotel, there's a frat party, the frat decides, hey, what's the maximum number of people we can cram in there? Worst case scenario, we're going to cram 20 people in there, average mass is 75. The elevator obviously has mass as well, because elevators that don't have mass don't sell very well, because that's known as air. And the maximum force that the cable can withstand and not break is 2.96 times 10 to the 4th newtons. So oddly enough, you're going to start with this, okay? So, you're searching for acceleration, okay? That's what you're trying to find. You know what the applied force is. That's that 2.96 times 10 to the 4th. You can figure out what the opposing force is by taking the total mass of the system and dividing it by g. Find your net force, divide that by the mass, boom, there's your acceleration. When you get over to page 2, okay, you're going to have a helicopter. You're going to have 2 different situations. One, you accelerate the helicopter upward at 1.2 meters per second squared, and then you're going to accelerate it downward at 1.2 meters per second squared. Obviously, which of those 2 answers is going to be bigger?
Upward.
Upward force. Why?
Because you're
Positive net force, and you're working against
gravity.
gravity. 15 and 16 refer to limb calculations. It's the same numbers, same mass, same G. You're just going to go through and calculate net force and applied force under different circumstances, and then you're going to do the same thing if it is on the Earth. Okay. Now, when you get to page 3, so let me kind of show you how this is going to play out. What you're going to do is you're going to take, like, this is technically what's called an Atwood machine. So my pulley system over there, that's technically known as an Atwood machine. So, Colin, give that a little bit of a spin so that you can get to here. Yeah. So, you take a pulley and a pretty good sized length of string. And what I would recommend is, if you don't know how to do this, I can show you. But I would tie like a simple loop on the end of the string. Just make the string come back like this. You got this. Make the squirrel run around the tree and then dive into the hole. And you got a simple loop like that. Do that on the other side. Doink, doink, doink. Boom, there you go. Okay. So, you're going to take this, you're going to put a 200 gram mass on one side, and then you're going to put a 200 gram mass on the other side, and what's going to happen?
Nothing.
Absolutely nothing is going to happen. Why?
Because Because they weigh the same.
They weigh the same, okay? So you're gonna have this action like this. Wow, physics is cool. That's gonna be a tough lab to do. Okay, that's not the point of the story. But then you're gonna take a 20-gram mass, and you're going to attach that to one side, okay? I'm gonna put a 20-gram mass over here. So when you do that, now what's gonna happen?
Obviously, the heavier one goes down.
So now when I drop it, so you're gonna hold it up like this, I'm gonna drop it. Now it begins to accelerate. So what you're gonna do, Sean, let me see your lab. So you're gonna take the 200 and the 220. You're going to pick a distance. I don't care what the distance is. I'd say at least maybe 30 centimeters. And what you want to do, and it has to be consistent. So you're going to do this and you're going to let go, and it's going to fall like this. So you can measure one of two things. You can either measure how far the 220 falls, or you can measure how far the 200-gram mass goes up. I don't care, pick one. Then you're going to measure the time that that takes, okay? So you're going to do this 5 times. Who's ever time, and again, you know the routine, I'd have at least maybe 2 people timing this. If you're timing it, don't be up here trying to guess when it crosses that mark. If you're timing and you've got a meter stick here, you want to be where you can see that at a right angle so you don't get something called parallax. So I don't care what you do. You're going to pick a distance. That's up to you. You're going to record your times. Now, if you're clever, what are you going to let the initial velocity of the system equal?
0.
0. Why?
Makes math easy.
Makes the math easier. Okay? So, what you're going to do, watch it. So, over here, you're going to write down whatever that distance is. I don't care what your distance is, pick a distance. You're going to calculate the acceleration. Okay, so underneath this data table, this is where you're going to put your experimental acceleration. Now, how are you going to calculate your experimental acceleration? You all have done this before. What are you going to use?
The numbers.
Okay, brilliant.
Way to go, Kevin.
And then we're going to use different numbers for the second trial.
Yeah.
And then very different numbers.
How about 1/2 AT squared plus V naught time?
Sure. Cool. I don't know. I'm not paying attention.
If you're
Yeah.
clever, and you are, what are you going to let the initial velocity equal?
0. Cancel out that V naught time.
You're going to know the time,
No distance.
you're going to know the distance, you're going to
Self
calculate
acceleration.
an experimental acceleration. You all have done this before. So this acceleration here is going to be based upon your data, okay? Measurement of time, measurement of distance. Now, then down here, this is where you're going to calculate a theoretical acceleration. So, you're going to have the 200 and the 220. So, when you look at that, and you got the 200 grams and the 220. Which one are you going to call the applied force, and which one are you going to call the opposing force?
The 220 applied.
Yes. So you're going to take this, you're going to find the weight of this, and you're going to call that the applied force. You're going to make this the opposing force. Okay? And then you're going to divide the total mass by the net force. You're going to calculate a theoretical acceleration. Then you're going to do the same thing with the 200 and the 240. So, before you even do the lab, what do you think is going to happen to the acceleration of the 240 and the 200 versus the 220 and the 200?
It'll accelerate faster.
Different acceleration.
Why should the 240? Why do you think the 240 is going to accelerate faster?
Because the force net's greater.
More force.
There is more mass. That's an interesting idea.
The force net's greater. Or the net force?
Why is the net force bigger?
Because there's a bigger difference between the two masses.
Just there's
But
no-
what else is increasing though? You said it.
Mass.
Total mass of the system is also increasing though, right?
Hmm.
Huh. So what's happening to the total inertia of the system?
Increasing.
It's also increasing. Huh.
Wait a minute.
Hmm.
Huh. Things that make you go,
Let's do science.
let's do science. So here's the balancing act. Yes, you are legitimately going to have a bigger net force. Okay, you are. Because you're gonna have 240 and 200 versus 220 and 200.
But it's
You're gonna have a big net
acting on
force.
a total.
But the question being is that the increase in mass and the increase in inertia going to offset that and you're going to get the same acceleration? Or is the increase in net force enough that you still end up with a larger acceleration? That's what you're searching for. So here's what you need to get through, and we'll take up the next part tomorrow. So we'll get through this third part, changing the angle. This we will deal with tomorrow. So basically, you need to stop at the bottom of page 3. So focus on getting your data. And I'm going to tell you right now, the toughest part is that one with the 200 and the mass is going in opposite directions. Okay? All right, I'm done. You're on your own. Be free. This one,
How does this make sense to you? How does this make sense? Because